those who wait. So without further ado, here's a topological notation for proofs and programs.
Thanks, Jimmy.
The question is missing a word.
Really?
Yes, system.
No, it's here, I think, no? So, well, thank you for, is it the right angle?
Yes, yes.
Okay. So, thank you, Jamie Sampson, for inviting me here. It's a really great opportunity. I mean, everybody doing semantics in the world thinks that Oxford is a very special place since Stretchy. I was reading an interview yesterday, and this is the place to be to discuss about kind of mathematical, topological approach to proofs and programs. And mainly, the talk is about trying to put together, let's say, linear logic and computational side effects. Okay, and well, in order to do that, maybe because it's a big problem that linear logic has many. It's a very beautiful framework where you have like proof nets, many denotational semantics. Now we know even how to do differential computations like Taylor formulas for computing proofs and interactions. But at the same time, side effects are a problem. We never really understood how to mix that with side effects. So this should be compared with what's going on in game semantics. Game semantics, you can integrate, describe many extensions, programming features. And the question is, well, is it possible? Is it possible to think logically and computationally at the same time and understand what's really, how linear logic should be adapted or relaxed so that we can then introduce effects? And in fact, thinking about it, well, you get this picture where, some kind of somewhat unexpected connection comes out with knot theory. So really the purpose of the talk is to explain what is called functorial knot theory a bit, okay? And then, well, to show that it's essentially what we are doing in semantics. So in a way, if you like, semantics is some kind of representation theory for programs, just like, if you like, computing invariance for knots is some representation theory for some kind of algebras, okay, or some kind of categories. So, well, if you think about a knot and if you think about a proof, well, they look like quite complicated, symbolic things where you can transform, like typically you can transform a knot by deformation and transform a proof by typically cut elimination or other surgery, symbolic surgery. And well, let's try to, in a way, describe that kind of proof here. So this is here described in the language of sequent calculus introduced by Gensen in the 30s. Try to see whether we could, in a way, extract, have maybe a more direct, immediate description of that kind of proof. So, for instance, here this is the proof of the so-called Drinker formula. Okay, and it's interesting because it's a proof in the formula is valid in classical logic. So here it's classical logic, but in fact it's possible to understand it using the tools I'm describing now. So, well, let's go and think about alternative notations for proofs. And well, a very very natural starting point is to think about game semantics, because in a way it's a very natural, very simple, basic interpretation of what a proof is. So the idea is that given a formula, every proof initiates a dialogue where proponent tries to convince opponent and opponent resists and tries to refute proponent. And we know, in game semantics, that well, essentially proofs in many logics may be described as such strategies, and maybe, and this is the starting point of this work, this should be, in a way, the very, it's more than just a notation, maybe that's the essence of a proof, okay? It's to be dialogue, or to initiate a strategy. And, well, in order to connect it to not theory, it's a good idea to start by thinking about the algebra of games. Okay. And what can you do on a game? Well, the first thing is, there is a duality between the player and the opponent, so that when the player plays the game A, then the opponent plays the game not A. And so if you reverse the board here, well, now this player plays not A and the player plays A. So negation has to do with turning boards. Okay. So and we will see that this plays an important role, this idea of negation. But of course, you don't only negate games, you also combine them. So the basic construction is to take two games here and some kind of pair. And the game that you define by pairing, by tensoring two games, is really a game where the two boards, the two games are played in parallel. Okay. So there are subtle issues about who's got the control here, but let's say essentially that one of the two players sees the two boards, whereas the other one, sees only one board independently of the other one. So, so there is a little dissymmetry between the player and the opponent, and we will come back to this a bit later. But essentially, it's putting the two games in parallel. Now, the sum is the game that you play like this. So you let player. So the first move of the game is to let player decide whether he wants to play this game or this game. Okay. And then once player has chosen, okay, well, everybody agrees, so opponent and player will count that game if player has chosen this game or this one, if player has chosen this other game. And putting all that together, we get something which is very similar to what one gets with vector spaces. When you have a vector space, you can consider its negation, so which is a vector space of its forms. Okay, so the forms on the original vector space. You can take tensor products, you can take sums here, and we will see that the algebra essentially works in the same way. So the important question is to understand what is specific about games. Okay, and this will be the point about that talk. So it's an attempt to reconstruct game semantics from the very algebra of tensor and negation essentially here. So I should give a brief history of games and linear logic. So the first category of games and strategies, so the category as games as objects and strategies as morphisms, was defined by Joyal in 1977. Okay, and then this was re-evaluated in the light of linear logic after it was. After linear logic was introduced by Jean-Yves Girard in the mid-80s, so Blas gave a model, which was not a categorical model of linear logic, and well, in this kind of turmoil of linear logic, came two models of say intuitionistic logic, or more exactly, the programming language PCF, one based on history-free strategies defined by Abramsky, Jagadezon, and Malacaria, and the other one based on innocent strategies defined by Island and Hong. But what happened at about that time is that the connection with linear logic became a bit unclear. So in a way there was kind of, I like to call, with big words, like some kind of schism, So people carried on doing linear logic, some other people carried on doing game semantics, but there was obviously a difficulty to connect them, and one reason that, that's the point I will defend here, is that in a way game semantics is more refined than linear logic, okay? And linear logic is some kind of degenerate case, I mean, but in a novel sense, okay? Just like, for instance, commutative algebra is a bit degenerate compared to non-commutative algebra. Okay, so there is an inequality more here, which is not in game semantics. But we can think of game semantics as providing some kind of logic. Okay? And the reason why there was this schism is precisely that people, like, especially, starting from this work here, people were interested to define game semantics for various programming paradigms. Okay? And this is not possible in a way to do it in linear logic for reasons I will explain. Okay? So then it was quite natural that game semantics took its independence in a way. And okay. But on the other hand, it's important that we have a logical view on game semantics. So that's the one I will try to develop here. But really, the starting point of this analysis of games is topology, and in particular the topology of knots. So what I will explain is that game semantics may be seen as some kind of refinement of knot theory, if you like. So, and the right place to think about it is these string diagrams, which define some diagrammatic notation for monoidal categories. So a monoidal category is a category equipped with a tensor product and a unit, and some coercions that describe how tensors may be reorganized. Typically, here you can bracket your tensor in this way and this way, and there is some coercion to connect them. And the point of string diagrams is that you may describe a morphism in a monoidal category as in this way, where typically you consider the entries here of the morphism and the outputs of the morphism here. And then what the monoidal category enables you to do is to build such diagrams by vertical composition, and this is the composition of the category. So typically when you compose here f and g, you describe it in this way, by vertical composition, and also by horizontal composition provided by the tensor product. So you see here, if you want to tensor this morphism with this morphism, you can draw it this way. And so an example is f tensor the identity. Okay? And this morphism, okay, f tensor the identity, may be precomposed with the identity tensor g here. Okay? So this is the notation for that. And the point about, the main advantage of this notation is that it's invariant under deformation. Okay? In the sense that if you take this diagram and you decide that you will, deform this, and so you want to consider, for instance, this diagram here, of course, you can describe it in this way, but it's not so clear that these two terms are equal. We need to look at it carefully. Whereas here, in the diagrams, it's obvious, your eye computes for you, if you like. And the point about monoidal categories is that they ensure that this equation holds. Okay? And, formally, this has to do with the fact that the tensor product is a bifunctor. Okay? So you can start by g and then f, or f and then g, and this is the bifunctoriality of the tensor product. And so that means that whenever you have such a diagram, you can reorder the little combinators, and the meaning is preserved. So in a way, string diagrams are some kind of very basic general apparatus which look a bit like proofness, okay, in linear logic. So I got interested in them because I was trying to understand proof nets, and well, they are in a way very natural and simple device for drawing morphisms. And I should mention that this extends, for instance, to functors. So, for instance, if we think about proof nets, we have proofs written as diagrams, and we have boxes describing the exponential modality. And here it's the same. We can, whenever we have, so a modality should be thought as some kind of functor, and we can, whenever we have a functor between two categories, we can draw little boxes like this. And so we can, well, here if you like, I mean, this is nice to think about it. Here, if you like, we are in the category D. So this is the codomain of the functor. And in the box, we are in the category C here. So the category C is blue here. Okay? And we have, I mean, equations between boxes. The monoidal functors will be described in this way with many inputs and one output. And this really looks like an exponential box in linear logic, because we know from categorical semantics of linear logic that the bank is a monoidal functor, so it should have like you know, these I mean many doors as input and one principal door as output. So usually in linear logic you would draw this with question marks here, so there are auxiliary doors, and this is the principal door with a bank. So you see, it's quite nice and very basic, but it's mainly used, or one, I mean, beautiful application of these ideas about string diagrams is in the description of knots. Okay, so let's try to build knots using this two-dimensional language offered by monoidal categories. Okay? So remember, now we have like our sheet of paper, and we can compose vertically and horizontally. So now if I have a knot which I draw on a two-dimensional sheet of paper, I can decide to Xerox it, you photocopy it. And whenever I see a combinator, like these ones, for instance, a braiding, I will indicate that there is a braiding, and I will do that. So in the end, my knot will be described completely algebraically, as a kind of set of generators floating around in the monoidal category. And the point so what I'm introducing now, like braided categories, ribbon categories, is that if we decide to deform the original knot, and then we Xerox it again, we get two different algebraic pictures, but we know that in any braided or ribbon categories they're equal. Okay? So let's see how we do that. So the first, very basic notion is a notion with of a monoidal category with a braid. So what is a braiding? It's a family of maps which transport A tensor B to B tensor A. And we like to draw them like this, okay, in the string diagram notation. Okay? And of course, these maps have inverses, and the inverses we like to draw them like this. And the reason is that, it's based on topological intuition that if we do that, okay, so this is gamma, maybe, and then gamma minus AB. Okay. Well, this should be equal to the identity. Okay, this is the identity. So, in a way, these notations are helping us. Okay. So they guide us, and what we want is that in the end, this notation, in fact, describes the equalities between our morphisms in a braided category. So typically here, this is topologically valid, if you like. Okay. So Now, when you have a braiding, you need to be careful about, so this is the braid. So maybe I should, yes, I use this thing here. So, So in order to present the braid group, one would typically consider, like for instance, with three braids, we have like sigma, or maybe gamma 1 and gamma 2, and the main equation is that gamma 1, gamma 2, gamma 1 is equal to gamma 2, gamma 1, gamma 2. Okay? So here we need, so this is a presentation of the braid group. We need to have an analog for braided monoidal categories. So here I describe the usual way to do it, which is a bit different. Okay. So in a way, this is the good way, and this is like another, I mean, it's quite amusing way to put this equality, which is to have as this diagram commutes, and which means pictorially that we have this equation. Okay. So in a braid group, your two each ribbon, if you like, is disconnected, but here you can connect them by the tensor product. So this equality here reduces essentially to this one. Okay, there is another one here. So there are two diagrams like this. And the point is that once you forced these equalities in a braided monoidal category, then you can reason on the braidings just like as it were real braidings. Okay? So there is a nice coincidence between the algebra on the one hand, which is provided by this kind of coherence diagrams, and on the other hand, the topology. Okay. So now this was for braiding, but in order to describe a knot, we need also to have dualities. So an object is a left dual of another object when you have these two generators here, and they satisfy these equalities here, okay, which are topologically valid again. Okay. So now a ribbon category is a category which is braided and such that you have these equalities here. So if you think about it, okay, they are valid even if this is not just a rope, but it's a ribbon. Okay, because here when you do that, it's a curve, so it means you twist your ribbon here twice, and here you twist it twice, but in the other direction. So these are also valid if you play it on ribbons. This is the reason why it's called a ribbon category. And the the theorem is that the free ribbon category is maybe defined as a category whose objects are sequences of plus and minus. Okay. So there are like words on plus and minus. And the maps between these objects are tangles. Okay. So that means that the equations that we put here, here, and here are sufficient to describe, they're complete if you like, from the point of view of topological deformation. Okay? So in particular, whenever we have a ribbon category, there is and a functor from category C into a ribbon category, this functor lifts to a semantic functor, if you like, so which associates to every morphism here in the ribbon category. So that means to every tangle, it associates a morphism here, which provides an invariant of the tangle. So in particular, if you consider the maps from the empty world to the empty world, they are exactly knots, okay? Ribbon knots. So this functor here will transport every knot to, but of course every knot, every equivalence class of knots up to deformation, okay, to a morphism here from the unit to the unit, and this morphism is an invariant, okay, of the knot. So, for instance, it's possible to prove in that way that the so-called Jones polynomial invariant, is indeed an invariant of knots. And as exercise, it's nice to see that this right trefoil and left trefoil, so you see they're equal up to symmetry, okay? But they are not equal up to deformation because this one has this invariant, whereas this one has this invariant, okay? So it's quite nice. So it's like intermezzo, okay, 5 minutes. It's quite nice to see how we compute these invariants, okay? So, of course, there is the category, theory, and everything behind, like a big brother, keeping, like checking that everything is right. But now we can play with this invariance, and it's something, okay, what is important is that invariants are important in semantics. When we do like semantics of programming languages, we are building invariants of programs up to execution. But these people in knot theory, they have tools that we don't really have. So, and typically this is the Conway equation. Okay, so it's something we should meditate on. So it provides a very easy way to compute the Jones polynomial of a knot. So what it says is it's very brutal. Okay, so imagine this is like a program. Okay, big program, and you say here I will change this variable into this other variable, or I will change this name of a memory cell into this other memory cell. We imagine that there is no relationship between them. Okay, what we had first and the second one, there are good chances there are lots of bugs coming out, and it's hard. But in the case of knot invariance, we have this equality, which was defined by Conway, which says that whenever you take a knot, and there is inside the knot this little picture here. So, we have this picture here. Okay. Anywhere in the knot, if we have a brain like this, we can brutally decide. We can brutally transform it in this one. Or this one. Okay. And there is this polynomial equation between them. So remember, there are Laurent polynomials. Okay, so that means you have inverse also on two variables, x and y. This is, typically, a joint polynomial is such a polynomial on two variables, and you have this equation here. So x times this invariant is equal to 1 over x, this times this invariant plus y, this invariant. And we can, and the other equation is that this trivial thing goes to 1. Okay? And then we can compute the invariant of this knot in this way by saying, well, very brutally, I will transform this little pattern here into this one and this one. Okay? So I'm really following my recipe here. And now, okay, since you've done this, this becomes the trivial knot, and this one becomes like two entangled loops, like this. Okay, so we know that this one is equal to 1. So we get this, and now we need to compute this one. So, okay, the first thing is, okay, this one is this one up to deformation, and we know it's an invariant, so we can do that. And so now we take this one and we apply our little recipe here, okay? So we get this and this. This is trivial. So we get this, and this is, I mean, these are two twin loops, okay? And now there remains to compute the Jones polynomial of these two loops, and it's not, I mean, it's not 2 or something, you know, it's not like you don't add the invariance by just opposing knots. It's more complicated, as you will see. In fact, I mean, a little computation shows that this is equal to this. And now from this you get, in the end, you get in the end, very basic computations, you get this one. Okay? And now if you compare it to the left straightforward, they are different, so you know that they are not equivalent up to deformation. So there is no way you can take, as long as you like, you will never be able to reorganize one into the other, because every time you do that, the invariant is preserved. So now let's try and think about what we do in semantics. So a traditional way to think about programs is to start from their functional kernel, so simply type lambda calculus. So thus from the notion of Cartesian closed category. So it's a Cartesian category with an arrow here, and this arrow here, this arrow functor, is defined by this natural equivalence, which says that there are just as many maps from A times B to C as maps from A to B over C. Okay, so typically the category of sets and functions is Cartesian closed. And then one can construct the free Cartesian closed category as the category whose objects are formulas like this, and the morphisms between the formulas are simply type lambda terms modulo beta eta conversion, and that's the way to build these simply type lambda terms. And from this comes the kind of prejudice that proof theory is intrinsically syntactical, because, well, this looks like very syntactical, yes? But now if you compare this picture here, which says that whenever I have a category and a functor to a Cartesian closed category, I can lift this functor to a functor which preserves the Cartesian product and the arrow, and which goes from this free category to this one. Okay? If we compare this familiar picture to the one we had before the intermezzo, okay. So yes, here is the same. It's exactly the same. Okay? So the question is, can we build something like this diagram, okay, in proof theory, but where this would be a free category, which would look like a bit like the free ribbon category. That means that it would be something like a topological kind of structure. And the idea is, well, yes, but it's natural, yes, but we need to replace the notion of Cartesian closed category by what I call a dialogue category, because it's a bit like a ribbon category, we'll see, but for dialogue games, where it's simply a monoidal category where you have a duality, and that means it's a negation, and negation means that there are just as many maps from A to negation of B as maps from A tensor B to bottom. Bottom is some kind of falsity, if you like, false object. And essentially that means it's like a symmetric monoidal closed category, but where there is just one object on which you can take the exponentiation. Okay? So negation of B, you can think of it as some kind of B row bottom. Okay? But you don't have B row A for every A. No, you don't have for every A. You only have that for a specific object. That's a dialogue category. So it's everywhere in a sense. Okay? So in particular, if we have a symmetric monoidal closed category, we have as many dialogue categories as we choose objects. You know, every object induces a notion of negation. So it's a very basic thing is so basic that the question is it interesting? Okay, apparently it's, okay. What can we say about it? But well, the first thing we should observe, okay, is that, okay, I mean, negation, another way to formulate it is that it's a category where you have such a bijection between the morphism between A tensor B and negation of C, and the morphism from A to negation of B tensor C. So there is a coherence relation on that side, but well, essentially it's this bijection that we're interested in. And so that may be, I mean, this may be drawn like this in some profunctor or distributor style, okay? But, and this has to do with Frobenius algebras. So, I mean, there are some abstractions I will discuss in the end, but let's say it's a very basic and maybe interesting notion to study. And, well, the point is that now, if we try to construct the free dialogue category, well, we can look at it in two different ways. We can say, okay, it's a logical thing, so it's a category whose objects are formulas, built with tensor product, negation, unit, and some variables, and then mapped between them are proofs, up to some notion of beta, eta equivalence, if you like. But there is also a more direct, in a way, or completely quite different way to look at them, which is to think about it just like with knots. Okay, so try to look for the generators and relations, if you like, of defining this this category, just like we did with knots. We had braidings, and then we had a coherence relation and braidings. We had dualities and so on. So let's try to do that for that notion. And what we get in the end is that, in fact, this may be seen as a category whose objects are dialogue games, and the morphisms are total and innocent strategies on these games. Okay, I should say that it's linear, so it's a specific notion of dialogue game where you don't repeat, okay, you don't replay a move. But, I mean, then, I mean, if we don't want to have nonlinear behaviors, we will have bang, okay, the spirit of linear logic, really. And if, yes. So let's try and extract the generators and relations of the category. So the first observation, and it's something well known in like the description of dualities, of that kind of dualities, is that there is an adjunction between negation and itself. So negation defines a functor from C up to C, the opposite category, but it has this functor has an adjunct which is the negation itself. Okay, and this comes from this equality that there's just as many maps from A to negation of B as maps from B to negation of A. And then this, we will turn it and we get this. So now, when we have an adjunction, we can present it by generators and relations. And this comes from Ross Street's work, so Australian, so what Street calls the formal theory of monads. And what one gets there is something really like the dualities we had in the case of knot theory. So the difference is that now, instead of having objects, we have functors. So we have, this is negation, but this is negation from the category to its opposite category. And this is negation from the opposite category to the category itself. And the fact that we have an adjunction means that we have a unit of the adjunction, which here says that every object, A, is maybe mapped into the double negation of A. Okay, so here is just the eta just says that you have a map like this. Okay. So epsilon says exactly the same thing. Okay. So it says that negation. Okay. It says something like this. Okay. But in C up. Okay. This is in C. This is the typical. It's a typical fact of logic. And here it's the same fact, but fact, the arrow goes in this direction in C. Okay. It's the same thing as this one, but seen in the opposite category. And okay, so that's the typical way to describe an adjunction between the category and its opposite category. And by the way, the colors here describe the categories themselves. So because we are building string diagrams not in monoidal categories, but in so-called two categories, the blue here is for the category C, and the red here is for the opposite category. And now if we try to describe the natural transformations, okay, from typically 6 negations to 4 negations, so remember each negation is a functor. So this is a big functor from C to itself, and here it's another functor from C to itself, and let's try to describe the natural transformations from this functor into this one, the canonical natural transformations. We get these kind of pictures, which are simply obtained by putting together these generators. Okay. So here it's a proof, if you like, that 6 negations of A implies 4 negations of A. Okay? Doesn't look, extremely exciting, because the logic is just a logic where you negate. There is no tensor product here, so you only have formulas obtained by negating something which is already negated, and so on. Okay? So it seems like very boring formula, but already if you look at the proofs of the logic, you have these things. Okay? And now there are string diagrams, so these little things are the functors. This is the unit of the monad, this is the co-unit of, the unit of the adjunction, and this is the co-unit of the adjunction. But now if we think about it and forget the colors, forget the string diagrams, only remember the flow of the functors, okay? What we are just describing is the game, the strategy associated to a proof in game semantics. Okay? Of course, in game semantics, we don't see the colors, but, well, except for that, essentially, it's the same thing. So now we know how to compose strategies in game semantics. It's something like this. You see, you have the strategy I was drawing. This is another strategy produced by putting together 3 units of the adjunctions. This is another one, okay? And really, what we would like to have in game semantics is that when R, which should be seen as an opponent move here, enters here, it follows that flow of information, you see? Okay, so it's a long way, and then when it comes back, it's like a player move. This is the answer of this strategy to this event here, to this opponent move. This is the reaction of the strategy. But now, okay, how does it work with string diagrams? Well, the point is that an adjunction is defined by generators, but also relations. And they are called the triangular relations. And the triangular relations, really, they provide the topology, if you like, required to transform this thing here into what we were waiting for. Okay? So in a way, if you like, the generators of an adjunction describe the strategies, okay, of the game, and the equations describe the dynamics of the game. Okay, so okay, we'll jump this. So still for the moment there is in a way it's nothing new. What we said is, okay, we have negation, there is an adjunction. From the adjunction I have string diagrams, and these string diagrams, they refine in a way the game semantics of a very poor language where the only thing you can do is just negation over negation over. But this also shows in a way that the canonical proofs between 2 such formulas are in a way simply defined or described by the fact that there is an adjunction. So the fact that there is that negation is adjoint to itself describes the logic, if you like, and the proofs. So now let's try to do the same thing for tensor and negation. So what happens when a tensor meets a negation? So we know something, okay, it's a good starting point, is that there is a strong monad somewhere, okay. So double negation defines a monad, and we have this map here, which says that the double negation monad, the continuation monad, is strong. Okay? So it means this tensor is able in a way to pop in, okay, this double negation And this is very important because this enables to think of continuations as like a computational monad in the sense of Moji, and in particular to describe how effects are distributed over a tensor, so over a pair typically of programs. Okay. But then is that all? So when a tensor meets a negation, is that all that we get? And well, I mean, one of the main observations of my work is that, in fact, it's, I mean, this strong monad is only, or this strength is only a particular case of a parametric strength. So what the parametric strength does is, well, just the same as here, you know, B enters into the double negation. Okay, so we have double negation of A tensor B. But now you may have an X here. So if X is the unit, you get exactly the same thing. Okay? But in general, you don't need that X is a unit. And now, what? I mean, why is this map so remarkable? Is that, in fact, it's a distributivity law. In the sense of linear logic, if you like, because you can think of it like this. It's X, so tensor is conjunction. So it says X or, so X or A, because there is, I mean, this is a tensor under a negation, so you can say it's an OR. Okay. And B becomes X or of course, there are negations everywhere around, okay? But if you like, the negations that are here are only putting control on this basic principle, okay? Of course, we don't really see the principle here because this simply says A and B implies A and B. So, okay. But here, if you kind of remove, remove the negation, if you like, you get this, okay? And in fact, that means that this, okay, so this is like for people aware of linear logic. This is, okay, this basic principle of linear logic, okay, in fact, is related to the strength of the double negation monad through this thing, okay? So you can think of this logic of tensor and negation, where negation is not involutive anymore, as some kind of refinement of linear logic, but at the same time, this is the place where, I mean, this notion of strength over the continuation monad lives, okay? So in a way, and the point is that, I mean, I discovered this little law here by thinking about this here, about linear logic. And what is, I mean, quite remarkable is that this distributivity law of linear logic, in fact, leads to a distributivity law of okay, what I call tensor logic. So it's just linear logic without involution of negation. It lives in two different ways. So the first one is, okay, so it's okay. You need to be a bit careful here. So R are the negations. This is a tensor. Okay, but there are negations seen as coercions, if you like. So this is a conjunction, this is a disjunction, and here you see we are able to transport this part of the formula here. Okay, so this is, and this corresponds to this distributivity law if we forget the fact that negation is non-involutive. But there is another way to lift. There's another distributivity law in this universe, which transports this junction here. Okay. They are really different, but when you forget the fact that negation, when you collapse it to linear logic, they're the same. And these two things, in fact, well, these two combinators, they live very well together in the sense that, okay, if you start from a formula X and you apply all these combinators to get a formula Z, it's always possible to factor a proof, because this is a proof but described by combinators, into that shape. And in fact, this is some kind of algebraic account of the notion of innocence. Because we know with, okay, an innocence strategy is a strategy which plays according to a view. So here, imagine that X is unit. Okay. In that case, these two maps, they are trivial, because you cannot apply this distributivity law and you cannot apply this co-unit on an empty formula. So you only get eta and this thing. And the eta, what it does is, you remember, eta is very basic thing. It does this, it does this plus that. Okay, so it's very basic. It's a very basic strategy. In a way, it's a story-full strategy. But this is the little combinator which produces the player views. So, if you like, these are the player views. And dually, these are the opponent views. So, in a way, this factorization theorem is a way to re-understand the notion of view in game semantics. And then, if we think about string diagrams, what we have is that, okay, remember in the monoidal category, we had the notion of braiding and the notion of duality, but the fact that duality and tensor commute in a way means that what we're we're describing a morphism as a way to transport a word of elements, so it's a tensor product of elements, into a tensor product of other elements. But here, because negation doesn't commute with a tensor product, it means that we need to consider formulas where we have tensor product and negation and tensor product and negation. So what we will do is, instead of transporting, if you like, a word, a tensorial word, into a tensorial word, we will transport a formula, a tensorial formula, so a tensorial tree, to a tensorial tree. So typically, what we have here is a description of this map, so one of the two maps which transport the double negation of A tensor double negation of B to the double negation of A tensor B. Okay? So let's see how to do that. So you start from the tensor product, so see that tree here. Okay? So these are the two negations of A and the two negations of B here, and the tensor product. Now you apply the strengths on the left, okay, that transport this double negation here to here. Okay? So now we have the double negation of A tensor double negation of B. Now we transport these two negations here, we get 4 negations of A tensor B. And now we apply the co-unit here, we get double negation of A tensor B. Okay? So you see, we've described a proof as a sequence of 3 combinators. Okay? And the point of the theorem here, the factorization theorem, it enables to show that 2 proofs are equal. Okay? If and only if the flow of negations are the same. And the flow of negation is precisely what the innocence strategy describes. Okay? So what I mean is that we have a diagrammatic way to do things, okay, but just like in knot theory, there are many ways to describe a knot. Okay? And here there are many ways to build a proof. But eventually, the semantics of the proof, if you like, is provided by this flow of information here. So, and that explains why it's possible to forget, in a way, these things and just remember about the flow of negations, and the flow of negation is the strategy played by the proof. Okay? opponent plays here, the strategy reacts here, opponent plays here, the strategy reacts here, opponent plays here, strategy reacts here. That's it. Okay. So by the way, there are two different proofs of this fact. One where you give priority here to the left branch, and then you play the right branch here. Okay. But there is also the other one, where you start by... Okay. And the fact that there are two maps here is really related to the fact that this monad here is strong. Because when you have a strong monad, there are always two maps from T8 tensor TB to T of A tensor B. Okay? And I will come back to, and this is the place where this study of negation meets linear logic. So what I will explain is that, okay, so we know that classical logic, okay, may be interpreted in intuitionistic logic by Gödel's translation. Okay, if you try to do that with categories, then what you get in the end is typically an order. Okay, so you start from a Cartesian closed category, you try to reapply the same translation. What you get is not a it's a category, but it's a degenerate category. It's just a Boolean algebra. So, can we do better? And that's the place where linearity comes in. So, okay, so this is, an algebraic way to think about Gödel's translation is that the negated elements of a Hating algebra form a Boolean algebra. Okay? But now if you try to do the same with a dialog category, so you have a category with a tensor product and non-involutive negation, you take the negated object, you don't get anything of interest. Okay? You get a category, but it's okay. But now, when negation has this additional property that it's idempotent, so the double negation monad is idempotent, and which is equivalent, in fact, to the equality of the two maps I was showing you. So it's equivalent in that case to the fact that the double negation monad is commutative. Then we have these equalities here. Okay. And these equalities, in fact, mean that we don't care at all. This equality is, in a way, is meaningless in game semantics. You will never, have this equality. But if you add it to your game semantics, in fact, that means you don't care at all about the order of calls. Okay. So what you get is a star autonomous category. So, and that's the typical way to build a model of linear logic. You start from a category with a negation, and then you take the objects which are negated objects. And when negation, when negating once is the same as negating 3 times, you get a star autonomous category. That's the way coherent space model, coherent space and like finiteness spaces or Köthe spaces. This is very important in linear logic. We know that in some sense. Okay? But here it's very formally explained. And so let's try and do that with game semantics. Okay? So in game semantics we have, or let's say with a non-involutive negation, we have these two maps here. And now the two maps from double negation of A to tensor double negation of B to double negation of A tensor B, they're like this. Okay? This is like typically the way we would write down in game semantics. And what is incredible in a way is that these two strategies are different in game semantics, but you can force that they are equal. And one way is, and that's the way I discovered that fact, is to play on asynchronous games. So instead of playing on trees, you play on some kind of asynchronous graph. And then the two strategies there. So this one, so this is opponent move, and then the strategy decides to play the left branch, then the right branch, and then conclude. And this is the other thing. So the point is that the two strategies are different, but when negation is linear, okay, you can fool your public. It's like a magic trick. nobody will be able to see the difference. Okay? And that's one key feature of PCF. Okay? So it's quite interesting that usually we say PCF is intuitionistic language. It's not true, because the constant, typically the Boolean constant of PCF, is linear. And that's the reason why, if you take A here is 1 plus 1, and here B is 1 plus 1, you get Boolean, tensor Boolean goes to essentially Booleans. You have two different ways to implement the strict AND. The left implementation, left to right, and right to left implementation, they are equal in PCF. And we know the reason is that there is no control. Nobody is able to interact with the two strategies and to stop them. Okay? And the fact that we don't have control in PCF is exactly the fact that the Booleans in PCF are defined like this. So it's linear negation. This is linear negation. Whereas in PCF with control, they are defined like this. Okay? So in particular, the difference between a question and an answer in game semantics is really here, in the modality. In the fact that we can, okay. So let's say, okay, so it's not tense logic like Manush explained yesterday. It's tensor logic, although I don't really care about the name, I must say. But what I care about is about the idea that, okay, so I was, okay, and I think maybe the community was prejudiced for a long time because I thought, maybe we thought, that linear logic is the origin of everything. Yeah, at least maybe in France. I don't know. But, so that means that game semantics was something that was a strange kind of linear logic. It didn't really work. What is the power? What is the tensor? It's not so clear. Okay. Now, the fact that the main ingredient in linear logic, which is the distributivity law here, of the tensor over the power, lives in two different ways in this tensor logic, so when negation is not evolutive. And that these two different ways correspond to the view, player view and opponent view, is the clear fact that, in fact, we should have a very logical and proud view of game semantics, in the sense that game semantics is a logic where you care about the order in which things are happening. And the fact that we care about this implies that we can add effects then. Okay, so I will just finish here. Okay, so for instance, it's interesting to think what would be the free dialog category, okay, typically, with access to the store, either the global store or the local store. And if you think about this question, it's very much related to the questions of full abstraction for Algol or ML-like languages. But it's formulated in a slightly different way, but essentially this is the same question. And what we would like is to, okay, what I think, I can't say we because I think it's a common question. It's the question of today is to understand exactly the relationship between typically the factorization theorems we have in game semantics and the monadic approach to side effects in Moji, or starting from Moji, but now with a nice reformulation in Lovier series, or with combinators. So typically the global store monad, we know that essentially it's described by operations of update and lookup, okay? And there are some kind of algebraic structure on the formulas, and maybe I should conclude with a little diagram, okay? So if one wants to make computational effects interact with game semantics, well, it's the same thing, because now, we know that game semantics has to do with continuations, as asking what happens when a computational monad meets continuations. Okay? And this question was, studied very deeply and nicely around Hyland and Plotkin in some kind of quite recent paper. And the idea is that, in fact, what you need is that the bottom, if you like, has some algebraic structure. So what does it mean is that typically you're able to, you have a map that enables to look up. Okay, so for every location, sorry, yes, that should be right here, so you can take, okay, so if you like, the fact that there is a computational effect around in the language essentially reduces to the fact that you have this structure on the response type, and so that means diagrammatically that we can do that kind of things. We can mix control, which is provided by Italo, for instance, of the double negation, with this kind of operations. Okay. So it's quite interesting to work very honestly on these combinators, trying to combine the combinators and then relate that to what we know on algol-like languages or ML-like languages in game semantics. And I think it's quite, it has a nice aspect of algebra and logic, and at the same time, it's a way to connect in a very deep and satisfactory way, I hope, to what we know about game semantics as well. Thank you.
So, do we have some questions? In front?
These 3D diagrams you have, are they the same as the 2D case in the sense that you're allowed to freely deform things kind of between the faces?
Yes. So the point of the coherence theorem is that when you have two different sequences of combinators which produce a proof, you're always able to identify. They are equal if and only if the flow of information, the flow of the functors, are the same. Okay. So it says that, in a way, this means that the system is sufficiently flexible so that you have that. Okay. Now, one thing that we don't have here for the moment is a theorem saying that there is indeed some topological structure up to deformation, which is the case with ribbon categories. So it's possible to prove indeed that if you see a braid as realized in R3 in space up to deformation, this corresponds exactly to the system we have. So it's an interesting question, but for the moment I try to attack it in some other way. Which is to think about Frobenius algebras. So I think this is I mentioned it very briefly at some point, but there is a connection with the Lax notion of Frobenius algebra, and this is really a topological object, if you like. So I would rather, I'm more maybe tempted to go in this direction, but maybe it lives already there. That would be interesting. But okay, the dream. Okay, if there is a dream, is that at some point we can say that there is a logical nature, a logical phenomenon, if you like, just like there is a physical phenomenon. So physicists, what they did is they transported it into geometry. Okay, so let's say the physical phenomenon is expressed in geometry. In logic, we don't have that, but with these notions of Frobenius algebras and cobordism, these connections, okay, what I would like to see emerge is some kind of, so game cobordism, and this is what we see here, in fact, but okay, I will explain it very briefly. So instead of having particles, like transported, evolving in time, there are games. Okay, so you can imagine your two Greek philosophers, meeting, and then it's a physical event. Okay, they discuss something is happening. It has a geometry, and then the question is, what are the side effects there? I mean, because let's say if you start from a Frobenius algebra, this has to do with the same thing essentially as linear logic. This is what Street tells us. But then it's difficult to plug the effects there, okay? Because you don't care about the order of events and so on. So now if you have a lax notion of Frobenius algebras corresponding to these games, then you can try and see what are the side effects. Okay, wow. This is not my talk, this is work in progress, but I think it would be very nice to have something like a logical phenomenon, or logical geometry. Wow. And maybe that would help to understand effect in some new ways. This should be optimistic.
Samson, do you have a question?
So discussion of tensor logic was basically at the multiplicative level. So to what extent does this go through to additive and exponential levels?
Yes, that's a good question indeed. So, okay. So the additives, I looked at them and quite carefully, and that looks quite, I mean, it's reasonable, okay? What is more, let's say it's what we expect, you know? I mean, we have like slices and things. One needs to be a bit careful. Yes, I should say something which I didn't mention it here, is that it's possible to add axiom links in the game semantics. So when you forget everything about negations, you get exactly the axiom links you had in linear logic. So this provides a guide to build the additives, and in a way the additives are mainly what we know in game semantics. I mean, you need to be a bit more careful. With the exponentials, it's quite subtle.
So I mean, so when you say that, you mean there's going to be, in some sense, lax versions of the additives. I mean, so there won't be products and co-products, exactly. I mean, is that the sort of...
So, for instance, okay, in game semantics, what you naturally get is, for instance, products, okay? Because if you open and start, it's quite natural to have
but then
products.
you get a problem with co-products.
Yes, so that's the point. The fact that negation, okay, is not involutive. What you would have is typically product in C and co-product in C up. Or, I mean, you can choose, okay? And this has to do with polarities. You know, negation is just another way to speak about polarities in games, okay? But the difference is that psychologically, we used to think that polarized logic is a fragment of linear logic. It's rather the other way around. So linear logic is a kind of depolarized logic. You see, that happens with your, I don't know, can you say that with your credit card? You know, like, it's depolarized, we say that in French. It doesn't work anymore. Well, but well, so in a way, although, I mean, so in a way linear logic is some kind of truth table for this kind of dynamic logic. And that's the reason why the usual way to look at dynamics in in linear logic is to speak about the geometry of interaction, which has to do with the axiom links. So the only dynamics that remains in linear logic, in a way, is the axiom links. Whereas here we have also the order of evaluation. So it's a beautiful invariant that we have with the proof net, but the question is what the things we can do there, can we list them? And we can do so much on them. But when it's lifted, then it becomes compatible with computational effects. And in a way, that's the way I like to think about all the things that happened, okay, in the last 15 years in describing programming languages with game semantics. I think we have a beautiful, a huge experience there. So if we can algebraize it a bit, and connect it to monad theory, it will be very, very convincing. That's the hope.
So we have a good supply of cookies. So, sorry, you have a question?
What you call dialog category, where you have tensor and negation.
Yes.
Isn't that the negation category used by hierarchical?
Again, I'm not. Okay, that's because what happened with so higher to some. So negation categories, as far as I remember, are okay. The first thing to say is we should not fight for words. Okay, that is okay. Because the notion is immediate. Okay. So what happened with Ayo's work? It was is that he was very interested in something which has to do also with how Cartesian product, so how you can repeat continuations, how you manipulate them, and that's related to, like control categories and other things. So here it's just kind of, it's just a linear version of what is called the response categories. So then, okay, so what I mean is, because it's something I find important, is just a basic structure. So I call it in this way because then it's like a ribbon category. You get ribbon diagrams, here you get dialogue diagrams. Then I should check, but I'm sure that, for instance, the fact that there is that negation is self-adjoint is in Ario's work, Tileke's work he knows so much about all these things. Okay? The point is that starting from linear logic and trying to rebuild everything, we can get a very comprehensive view on all these questions, and they are subtle. So, for instance, for instance, control categories. If you look at game semantics and control categories, at some point people forgot that there are answers and questions, because when you have a control category, you have Cartesian logic. It's a fragment of intuitionistic logic. Linearity disappeared completely. So looking at it more carefully, saying that I have a linear negation, I have a bank, you can reconstruct polarized logic. Polarized in the sense like control categories, but now you can say where you put the bank. And this is very important to understand the difference between intuitionistic logic and classical logic. So classical logic is a situation where you put the bank above existentials. So, sorry, maybe it's somewhere, maybe not. Yes. So if you look at the basic the formula here. Okay, the reason why this works is that in this tensor logic, is that you do that. Okay, you interpret this formula. Remember, this it's a kind of a priori. We need to do that. If we want to describe a formula as some kind of game, it means we have to interpret it in the logic of games. Okay, so here, if we interpret it, we get this. This, you can say it's like something like this, but and the fact that the formula is valid in classical logic but not in intuitionistic logic is that dynamically the prover can backtrack to this position thanks to the bank. Okay, if you remove the bank here, the formula is not valid anymore. Okay, because the proof of the formula is this is the Drinker's. Because formula, I'm sure many people here know about this formula, so maybe I should, before the drinks. So the formula says, this is much better in Britain, because in France we say café, or here, let's enter a pub, okay? And there is a customer which is extremely sober, because if he drinks, okay, so A means, this means Y drinks. If he drinks, then every other customer drinks. So he's really sober, you see. Of course, if you enter into the pub, you will never find someone like this. Okay, so, but still, I can prove it, interactively. So, and how do I do that? So suppose I want to prove that. So I enter the pub with you, okay? And I say, well, let's pick anyone like, Jonas, okay? You're extremely sober, so you should drink, okay? But then the adversary says, but no, come on, he's drinking. But this other one is not drinking. So I have a counterexample to your statement, okay? But now, you opponent, you found someone who's not drinking, so he must be very sober, So I said, okay, sorry, I was wrong. I should change my witness, okay? So I backtrack in the game, and now I give a new witness. But in order to do that, I need this stuff here. And the problem with, let's say, this kind of analysis becomes, you can make that kind of analysis if you have a bank here. Okay? So that means it's quite nice to have a linear negation, just I give you the hand, and then when I want, I can add a bank. And that's a way to also explain the difference between PCF without control and PCF with control. Okay? PCF without control, I mentioned it during my talk, but PCF without control is interpreted like this. The booleans are like this. And this is the interpret. So imagine negation is involutive. This is the interpretation of the booleans in linear logic. And now another interpretation is okay, with a bank here. And this is the interpretation in the CPS translation. Okay, but the CPS translation, because the CPS translation traditionally is not linear. So if you have a linear CPS translation, you can say that, but if you don't, then you need to do that. And this is really the essence of control categories, polarized linear logic, and LC, and GR's work on polarities. So we can refine it, and here this is a question, this is an answer, because you need to answer a question when it's linear. Here this is a question, and this is a question because you don't need to answer. It's a move. Rather than a question, I should call them, they are moves. But there is no, if you think about it, a question, the difference between a question and a move is that you want an answer. Okay? That's it.
Okay, so thanks. There's plenty of cookies, so if anyone would like to come to the corner room, eat them, have more discussion, that would be great.